Hello, everyone. It's my pleasure to present at the SPA 2021 conference our work on the I/O lower bounds for statically analyzable programs. In short, in this work, we took the computational directed acyclic graph pebbling abstraction and used it to significantly improve the previously best known I/O lower bounds for important scientific kernels. Moreover, we then analyzed the larger programs which were never analyzed before from the I/O perspective, deriving important data movement optimizations. And data movement is all you need, not only because the arithmetic intensity decreases with stencil computations, sparse data structures, and irregular computations, but also because nowadays architectures deem constant steady data stream to fit GPUs, tensor cores, or FPGAs. And this is often all embedded with large distributed systems where the communication between the racks can be a performance bottleneck. So in short, we could say that in general, the less data movement, the better the performance. And here I would like to clarify what do I mean by data movement. So in a distributed setting, the data can travel both across the memory hierarchy vertically, as well as between the parallel processors horizontally. And here we take the perspective of a single processor equipped with a small private memory, and every piece of data is either residing within this private memory, so it's local, yielding no I/O cost, or it's somewhere else requiring the I/O operations. And in this work, we want to bound this I/O cost to bringing this data to and from the private memory. And to do so, we take the Red Bull Pebble game abstraction introduced by Hong and Kung. And there, the I/O cost of a schedule is the pebbling cost of a corresponding CDAG. And to bound this cost, we take a look at some subsets here. And for each such subset, we can construct a dominator set, in some sense, a bit of an input set. And if the size of the fast memory S is, for example, 4, and the dominator set size is twice the size of the memory, then what happens? Then having these 4 pebbles, they can occupy at most 4 of these vertices in a dominator set. So the remaining 4 vertices have to have blue pebbles. So they have to be in this somewhere else location, yielding the lower bound on the loaded elements. Now, knowing this lower bound, we just need to count how many of such subsets we need to cover the entire CDAG, and we can derive the total I/O bound as the minimal I/O per subset times this numbers of subsets in the partition. Now, this work was extended several times by different authors, and here we take the path of the X-partition abstraction presented at the Supercomputing 2019 conference. So here the observation is that if we take a look at this subset, let's call it subcomputation H. The size of the subcomputation H is a function of the size of the dominator set size. So here the dominator set size is 8, and the size of the subcomputation is also 8. Now, if we parameterize the size of this dominator set and we increase it, for example, by 1, then by incurring just 1 additional load, we can pebble 4 more vertices. So this ratio between computation and I/O changes. So if we just keep the size of the dominator set as a parameter, x, then we can design the total I/O lower bound as v, so the total number of vertices in a CDAG, divided by this computational intensity. Now, the main question is actually how to find this size of this maximal subcomputation H max. So given the size of the dominator set x, what would be the maximal possible subcomputation we can construct with this constraint? And that was left as an open question in the original paper, and the authors were only able to devise this function for the simplest possible case for the matrix multiplication. In this work, we endeavor on a quest how to generalize this result, how to find this function for a large class of programs. Unfortunately, in the most general case, this is p-space complete. So we need to limit ourselves to a broad enough class. And here where the SOAP, simple overlap access programs, come in. So Let's take a look at an example of such class of programs. So what we can see here is that we have some arbitrary loop nests. This loop ranges can depend on the outer ranges. And we have some computation here, which as an input takes some static arrays, and the output is also stored in some array. So this looks very much like a polyhedral model, which is very popular in a compiler community. However, here we extend the polyhedral model, for example, allowing non-affine accesses to the array. So as long as the accesses are injective inside the domain, we're good to go. Also, the ranges can be any countable sets. So again, we are not limited to the polyhedral model. What do we have here? We also can have multiple arrays, and we assume that they are disjoint. And we can have multiple accesses to the same array as long as these different accesses are offset by a constant vector. So here, for example, this I is offset by -1, 0, and 1. And this is a defining property of the SOAP. So within this class of programs, we can positively answer the question how to bound the size of the maximal subcomputation given the dominator set size as a parameter. Well, how to do it? So this is one of the main contributions of the paper. And now I would like to present the intuition behind our key lemma in the paper. So let's take a look at this example here. Recall that this iteration domains can be arbitrary sets. So let's put these elements of these sets, D1, D2, and D3 visually here on a screen. And now the question is, what would be the upper bound on how many unique ijk tuples we can create given these elements of the sets D1, D2, and D3? So for a fixed element of D2 and D3, we can have at most 3 different ijk tuples, and we can repeat it for any combinations of these subsets. So this forms the upper bound on the number of unique ijk tuples here. So of course, the iteration space can take arbitrary shape and can be much smaller, but still this construction will serve our purposes. Now, the next key observation here is that for the fixed ijk tuple, we can uniquely identify the input vertex from array A, array B, and array C. So this is how we construct our CDAC. Now we need to find where is our subcomputation H. To do so, we can pick arbitrary subsets of D1, D2, and D3. So let's pick 2 elements from each of these subsets here. And now we can use, again, a combinatorial machinery to upper bound the size of the subcomputation and lower bound the size of the dominator. So here the subcomputation are these blue vertices and the dominator set are these orange vertices. Now let's put it a bit more formal. Recall that X is the size of our dominator set. Now what we would like to do is, given this parameter X, we'd like to find the size of this maximal subcomputation. But this is not what we can do yet. Instead, we have to start with, given the sizes of our arbitrarily chosen subsets here, this D1, D2, and D3, so we can pick them however we want. So given this as a parameter, we want to find the sizes of the dominator set and the subcomputation itself. So the dominator set is hidden here with these orange vertices. In the top right corner, this is this set. And the subcomputation, here are these blue vertices. Again, on the top right corner, this is this blue set here. Now, to bound the size of the dominator set, so this is lemma 3 in a paper, we have to consider all possible overlaps allowed by the SOAP definition, because recall that we can have, for example, stencil-like accesses which overlap. And then we want to find a tight lower bound on the union of these accesses so that we can prove that this is absolutely guaranteed minimum of the number of accesses that we have to perform such subcomputation. Now for the subcomputation itself, this is lemma 4 in the paper, we have to use combinatorial methods to enumerate all possible subsets created by our D1, D2, and remaining subsets to maximize the size of the subcomputation for the fixed size of the input set. Now, equipped with this result, we can proceed further and solve this optimization problem using KKT conditions. So what is happening here? In a previous step, given the parameter d, we looked what would be the value of x. Now, having solved this, we reverse this process, and now we treat x as a given parameter, and we want to find the d as a function of x. So here we have the size of our subcomputation hidden in this maximization function, and the size of the dominator is the sum of these three vertex sets here. Now, having solved that, recall that this is true for any value of x. So because we want to find a tight lower bound, we want to maximize the lower bound, so find the x such that this value is maximized. And this is how we finally derive the IO lower bound for such SOAP statement. So here d is the size of the entire CDAC, and the dominator set is here in this numerator, and the size of the subcomputation is in the denominator. And this alone is enough to improve several previously best known IO lower bounds. However, in reality, most of the programs will contain multiple such statements that can possibly interact. And let's see what would happen if we introduce a second statement here. So we can analyze both the statements separately. For example, for the statement 1, we can see that we have these two accesses to array B and array A, and we can use lemmas 3 and 4 to design the computational intensity rho and the IO lower bound Q. And we can do the same thing for the statement 2. Again, deriving rho and Q using lemmas 3 and 4. But observe now what is happening. The output of statement 1, this array C, is the input for statement 2, and this data can be possibly reused. So let's see how it would look like. If we draw the CDAC for a very small case, then it would look more or less something like this. So recall from the previous slide that this array C is computed by statement 1, and its computational intensity is the size of the fast memory minus 2. So what does it mean? It means that for each load operation, we can recompute S minus 2 elements of C. So the IO cost of computing C is very, very cheap. So instead of storing and loading these elements, we can basically recompute C on demand. And this can possibly alter the total IO cost. So let's formalize this observation again. And to find the lower bound for such program, we need SDG, symbolic directed graph. And this is a graph where every vertex is a program array, and every edge is our access function as created by the SOAP definition. And on this SDG, we can do the SDG partitioning of the non-input vertices. So how would it look like? Well, we have one possible partition here with two connected components here, and such partition corresponds to a schedule in which both statements are executed separately. So first we execute the first one, we flash the memory, and then we execute the second one. Okay, and then the IO cost would be the sum of the IO costs of these two statements. But there is another possible partition here, namely when we just have this one subset, C and E, and such a partition corresponds to a schedule in which these two statements are executed together. We have a kernel fusion here. And for such a subset, we construct what we call as subgraph statement on the induced subgraph, for which the inputs are the inputs of this induced subgraph. So here observe that now array C is not an input anymore because it's within this subgraph. And for this, we can construct our SOAP statement collecting all these array accesses which are output here. And finally, we can use our lemmas 3 and 4 to derive the computational intensity and the I/O cost for this statement. So here, observe that by merging these kernels, the total I/O lower bound is asymptotically lower than if the statements are executed separately. Now, we implemented our SOAP analysis in Python language, and the entire pipeline looks more or less like this. We take the input program written in C, we compile it with the DAIS data-centric compiler, which creates this intermediate representation exposing explicitly all the data movement. And we take this intermediate representation and use Python to create our SDG. And on this SDG, we can perform our mathematical analysis and automatically derive the I/O lower bound. So for example, for this kernel, finite difference time dimension, the automatically created lower bound is already 14 times tighter than the previously best known lower bound for this computational kernel. As a bonus, actually, we can also get some compiler optimizations. For example, we can get for free the tile sizes. So the spatial dimension should be tiled with the size of square root of fast memory divided by 3. And we have the powerful information about the kernel fusion, so which kernels should be executed together. We evaluated our implementation first on existing bounds and see if we can reproduce them or improve. As a first step, we take a look at the polybench polyhedral benchmark suite. And all these kernels were analyzed from the I/O perspective by Oliveira et al. Last year, and also on the direct convolution, for which the lower bound was derived by Zhang et al. Also last year. So what we can see is that for simple kernels and linear algebra, quite often we are able to improve the existing lower bounds by a factor of 2 or 3. But what is actually more interesting is that for stencil-like computations, where we really have this non-trivial simple overlap access, then we can improve this bounds by sometimes a factor of 14. Well, inspired by these results, we went further and wanted to examine larger programs that were never analyzed before. And we took a look at deep neural networks, unstructured grid simulations, and weather code. So for 7 such programs, we derived I/O lower bound using our methods. And to see that these programs are really much larger than Polybench. For example, LeNet5, the entire DNN, is almost 3 times larger than the largest kernel in Polybench. And usually Polybench kernels contain around 3 or 4 nodes, maybe 5. So to conclude, in this work, we designed the entire pipeline, which takes the input program and abstracts the schedule using the Red Bull Pebble game, X-partitioning, SOAP, and then we create SDG to capture reuse between the statements. And on this abstraction, we are able to create I/O lower bounds for the input program, also yielding important optimizations like tiling and kernel fusion. With this framework, we extend the polyhedral model for non-affine accesses. We improve existing lower bounds for long lists of kernels, as well as we are able to design the I/O lower bounds for previously unanalyzed kernels. We support our analysis with a thorough mathematical model, as well as we provide the implementation in Python, and we support it with the thorough evaluation on existing and new lower bounds. Thank you very much for your attention.